Hello. Okay. So the natural number component family allows you to manipulate what are known as natural numbers. The big caveat here is that they must be non-negative integers. So when you're working with natural numbers, which you will do quite often, you cannot use negative numbers. It is positive numbers only. Unlike an integer variable, a natural number variable has no upper bound on its value. So if you remember when we were talking about integers, they had a maximum value of like 2.14 trillion or something, a very high number. And if you went over that, you got a overflow error and it would loop back around and you would get weird things happening with your program. Natural number is our defense to that, how you can use numbers that are larger than the integer limit. So that's the benefit. The drawback is that you need to call methods to do arithmetic on them. So if you have an integer variable, say I is equal to 4, you can do fun things like I plus equals 4, or I minus equals 2, or I equals I times 4. You cannot do that with natural numbers. You have built-in instance methods to call on the natural number in order to modify the value of the natural number. So a little bit more difficult to work with than integers, but the benefit is that you can use as many digits as you want. So you can store, I don't know, a lot of values. Okay, here's that diagram that I was talking about, the interfaces and classes. So anytime you see a green circle, you should be thinking contracts describing what it should do. And then anytime you see the blue rectangle, you should be thinking actual implementation of that class, providing value. So looks a little bit different because we have multiple levels of interfaces in this case. So we have standard, and then we have natural number kernel. We can say n kernel. And then extending that, we have just regular natural number. So I'll just call it nn. And then we have nn1 and nn2. Okay, natural number 1L. Yeah. Okay. Okay, so beginning at the highest level, we have what's known as the standard interface. And the standard interface describes 3 methods: clear, new instance, and transfer from. And this is an important concept. Now, when we say that the natural number kernel extends standard, we mean essentially that it has all of the methods that are in standard as well as some other ones that may be described in natural number kernel. What do I mean by that? Well, any interface that extends the standard interface will include these 3 methods. And spoiler alert, every single class that we work with is going to have an interface that extends the standard interface. This is because instead of simply defining a clear new instance and transfer from contract in every single interface that we want for every single component, think natural number kernel or natural number or XML tree or simple writer, simple reader, stack queue, a bunch of other ones that we'll get into. What we can instead do is factor out all of these very important methods, clear, new instance, and transfer from, include them in a standard interface, and then have all of the other classes extend from that standard interface. So instead of creating, I think there's 18 OSU CSE components, instead of creating 18 different versions of clear, new instance, and transfer from, we factor it out into the standard interface and then have all of the other components extended so that it can include these 3 methods without having to redefine them every single time. This goes back to that idea of single point of control. So if, say, we wanted to add something to all OSU CSE components, the only thing that we would need to do is add it to the standard interface. And then since all of the classes sort of flow down from that standard interface, they would all get that method that we've added. Okay, so standard has contracts for 3 methods: clear, new instance, and transfer from. And we'll get into what they do, but any OSU CSE component that you use is going to be able to use these methods because they all extend the standard interface. It is the grandfather of all OSU CSE classes. We'll talk about what they do, I believe, eventually. Extending from that, we have natural number kernel. Now, today I said that we were going to talk about natural number. Natural number kernel is, in a sense, the minimum viable product that is needed in order to reason about a natural number. So anything that you would want to do with a natural number, you could do or you could accomplish using the natural number kernel methods. But it would be difficult, annoying, and very tedious, which is where we get into the actual natural number class. So natural number kernel has contracts, again, just contracts, not actual implementations for any of these methods, but for multiply by 10, divide by 10, and is 0. So again, any natural number that you make is going to be able to use these three methods. And these define what is the minimum viable natural number. So if you want to create a natural number, these are the three things that you have to have in order to be able to actually modify and use a natural number. But if you just use those three methods, it gets quite tedious. So natural number has 14 other methods, such as add, subtract, etc. Don't worry, we will get into pretty much all of them. That's why this slide is 100 long. Okay, how do we feel so far about natural number? On a lovely Tuesday afternoon, morning, not afternoon. Okay, so like I said, the interface standard has methods that are part of most or nearly all OSU CSE component families. And again, separating these standard methods into their own interface means that these highly reused methods are described in exactly one place. So instead of having a natural number clear, a natural number new instance, a natural number new transfer from, we just have a generic clear new instance and transfer from. We described exactly how clear new instance and transfer from should work, again, in a contract. And then when we get actually into the weeds of things and the implementations, that's where we can define how clear should work for a natural number, how new instance should work for a natural number, how transfer from should work for a natural number, as opposed to clear new instance and transfer from say, an XML tree or a simple writer or a simple reader. Again, these are just contracts, not describing how it's actually going to get done, just describing what should be done. Okay. The design goal and software, so single point of control. So again, if say we wanted to modify how the contract for clear worked, we could do that, and then it would update or propagate throughout all of the OSU CSE components. And that gives you a single point of control over all of the classes. So then we talked about the kernel interface is a minimal set of methods that are primitive in the natural number component family. Again, just saying that if you want to make a natural number, these are the things that you must include. And the natural number includes things that are nice to have. And then we identify them as special by separating them out into a kernel interface. And this should say that. So natural number has something like 18 other methods. But since, we'll get into this a little bit later, but we use the keyword extends here. So we say that natural number extends natural number kernel, which extends the standard interface. The natural number interface is going to have all of these methods. So natural number is going to include all of these methods because it is inherited from the natural number kernel class, which is inherited from the standard class. Natural number kernel is going to have all of these classes or all of these methods. Again, because it inherits all of these from the standard class, and then standard is only going to have these three. So as you get further down the tree, you gain more and more methods, you gain more and more functionality the further you go down. Okay, the choice of kernel methods is a key decision by the designer of the component family. And what we mean by that is you have to choose a minimal subset such that you can do everything that you want to do with a natural number, but not anything else. So methods such as add or subtract are not included in the kernel because there are ways to complete those methods, the adding of two natural numbers, the subtracting of two natural numbers, using only multiply by 10 and divide by 10. And I don't think you have to do it in this class, but you have to do it in software too. It's annoying. So, okay. Then the natural number has all of the other methods that are convenient to have in the natural number component family. They're often more powerful than kernel methods and are introduced to make the component family readily usable in typical client code. So these include things like add, subtract, divide, power, multiply, a bunch of others that we'll get into. But yeah, Okay, I think that's the basic overview of a natural number in terms of the class structure. Questions on that? Cool. Okay, so now let's talk about the mathematical model. If you remember, back to primitive types, we talked about mathematical models. We said that integers modeled integers, doubles modeled real numbers, booleans modeled bools, so on and so forth. That practice does not change just because we're working with reference types now. So natural numbers are modeled by this idea of a natural. And in the formal contract language that we've been using, we say that natural is an integer, and then we give an exemplar n, where the constraint is that n is greater than or equal to 0. So there comes back that idea that natural numbers can only be positive, or I guess 0 in this case. And then finally, at the bottom, we say that type natural number, the type of this class, is modeled by this idea of a natural mathematical model, which is all values that are 0 to infinity. Okay. Define the mathematical model, including any constraints. So the constraint in this case is that n is greater than or equal to 0. We say that natural number variable has a mathematical model. So natural number is modeled by natural, and so on and so forth. Okay. I'm going to erase this. Okay. So remember back to constructors. Constructors are how we tell Java how to make a certain class. Natural number has 4 of them, as opposed to, think, simple writer, simple reader, which had 2, and then XML tree, which I think just had 1. Natural number has 4, which is cool. So, as always, the name of the constructor is the name of the implementation class. Constructors differ only in their parameters, and each has its own contract, which is in the kernel interface. So when we say that the name of the constructor is the name of the implementation class, we mean when you make a natural number, you do the following. You say natural number, or to make a variable of type natural number, we'll call it temp, equals new, and then you have to provide a name of an implementation class. So in this case, I'll say natural number 2. And then in these parentheses are going to be arguments, and the arguments will determine what constructor you want to make. So beginning with the most basic, you can have a blank constructor, which will just give you a natural number with a value of 0. So this is the no argument constructor because we are providing it no arguments, nothing in the parentheses. We'll simply return to you a natural number temp, which points to a value of 0. Natural numbers are reference types. So instead of, say, an integer, which, say we had an integer temp here, the value is stored directly in memory where temp is defined. Reference types are a little bit different in the sense that where the variable name is defined is not actually the value that is stored. It stores a reference to that value. And this seems counterintuitive now, but is fundamental to the idea of a reference type versus a primitive type. So this right here is for all primitive types. And a natural number is a reference type because you're storing a reference to the value as opposed to the actual value. Okay. So, for example, if we have a tracing table here with our natural number, which is, well, not exactly. They call it n instead of temp. But what will be the value of n after this runs? Yes, 0. Thank you. So afterwards, the natural number n is going to be equal to 0. Cool. There is a constructor with 1 parameter of the same type, so natural number. So if we have a temp natural number, and then we would say the same thing, say we call it temp2 equals new natural number 2, and then into parentheses, we provide it with temp. It will simply have the same value as the temp natural number that we pass into it, or as the natural number that we pass into it, in this case, the value temp. So if we have a natural number m, which is equal to a new natural number with the value of k, what will be the value of m after this code has run? Somebody said something. What was it? Yeah, I'm not going to make you write it out, but it'll be whatever this long number is, which, as you can see, it is. Okay, constructor from an int. There's a constructor with one parameter, int I. So instead of passing a natural number, you can pass a 3 equals new natural number. You can pass an integer, say 42. Where might this cause issues? Yes, that is actually, I didn't even think about that. You can't pass a negative number. It requires that I is greater than or equal to 0. What is another case where this would cause an issue? Yeah.
Magic numbers?
No, not in that sense. Although it will still flag you for a magic number if you try to pass one in. Think about the difference between what we're allowed to store in integers versus what we're allowed to store in natural numbers. Yeah. So if you tried to pass in 1 with like 1,000 zeros in it as the integer, Java's going to get angry at you because that integer is not allowed. So you have to make sure that the integer is within the integer limits if you're going to set it from an integer. Later on, there's a method where you can convert a natural number to an integer, and you have to make sure that the natural number that you're working with is less than the integer limit, because if you try to shove a natural number that is bigger than the integer limit into an integer, there will be no space, and Java will get angry at you. Yeah.
Quick question. So the little hash marks mean like the same as the one
Yeah.
above it. Would that mean natural number 10th and then the number 2 after it, or is it just natural number 2?
Yeah, it should just be 10 2. That's my bad.
It's cool. I just wanted to be sure that when I go back to look over my notes, I'm not like, what is it? What am I looking at? Okay. And that would apply to the other side. So it's a new natural number 2.
Natural
In
number 2.
parentheses.
The only thing that changes is the parentheses.
Okay, cool.
Is what's in the parentheses.
Yes, got it.
Okay. That is 3 out of 4. So we have natural number n equals new natural number 2j, where j is an integer 13. What will be the value of n after this code runs? 13. Thank you. It will be the value 13. And then finally, there's a constructor where you can take in a parameter, which is a string s. The requires clause here simply states that there exists n to natural such that s equals toString n. This is a bunch of technical jargon. That means it has to be an actual integer. You can't just pass in like you can't pass in like this and then say, oh, why is it not a natural number of type 2? It has to be a string with an actual value. And this is how you get around the idea that you can't pass in an integer that is greater than the integer limit. You can pass in a string, which is a string of an integer that is greater than the integer limit. It is a bypass, if you will. In other words, S must look like the result of converting some natural number value to a string. And the natural number value resulting from the constructor is what you would have, what would have given you that string. So our example here, natural number n equals new natural number 2 with a value of s, where s is a string representing 265. What is going to be the value of n after this constructor runs? 265. Thank you. And s remains the same. Okay, those are the constructors. Now we're going to be talking about the instance methods. Instance methods, if you remember, different than static methods, must be called on an object of type natural number. So any of the methods that we talk about are going to need to be called on a natural number in order for it to work. So all of them are of the form n.method name with arguments, where n is an initialized variable of type natural number. So you cannot just simply call the method. You must call it on something. Okay. Recall, terminology alert. N is called the receiver for all instance methods. The corresponding distinguished formal parameter implicitly has the name this. So when we're talking about instance methods, anytime we call, say, n.add, then we pass in, say, I don't know, foo, which is another natural number. When we talk about the natural number on which the method is being called, we refer to it as this, the keyword this. because we don't know what the name of the natural number is going to be. I could have called it N2. I could have called it Steven. I could have called it Sammy. I could have called the natural number anything. So when we talk about it in contract language, we refer to it as this because this will take the place of, the variable name will take the place of this in formal contract specification. Cool. So the methods are introduced here, starting with those you might expect to see as a client, somebody who's going to be using natural numbers, and then proceeding to ones that might seem more surprising. There are a bunch of others that are not discussed for brevity, such as set from int, can convert to int, to int, set from string, can set from string, increment and decrement. If you would like to see the contracts of those, they're on the OSU CSE Components API, and they will give you all of the fun formal contract specifications for all of these. But some of these might be useful. For example, if you have a natural number and you don't know what the value is, and you want to know whether or not you can convert it to an integer without having to deal with the fact that it might be over the integer limit, you could use can convert to int. And once you do that, you can call toInt, so on and so forth. Okay, add is a void method, so it doesn't return anything. It adds n to this, it updates this, and it ensures that this is equal to the old value of this plus n. When we're working with contracts, this hashtag means old value of. So if you were to read it as if you were reading just a plain English sentence, you would say this equals the old value of this plus n, which is how addition works. We'll talk about parameter modes. This is the first parameter mode I think that we talk about is updates. So we said that this is in updates mode. So it's in updates mode, meaning that it will be updated after the method has been called. The default, actually, I'm going to write these up here. So we have updates. May be updated. And then if a variable is not specified in a contract to be anything, it is what is known as restores mode, which means it will stay the same. These parameter modes are a way to look at just the contract. Every single variable needs to have a parameter mode. And if it doesn't, then it simply just restores mode. And it's a way to look at the parameters or the arguments of a method and sort of reason about what might happen to them. So if I were to just look at the contract, I see that this is in updates mode. I probably can assume that it's going to be the natural number that is being added to. So updates says it may be updated. Now we say it may be updated because what happens if I just add a 0 to this? It's not going to update the value. So that's why we say it may be updated. And then again, that hashtag simply means the old value. So the old value of this plus n equals the new value of this. Parameter mode updates might be changed by a call to the method. If this is an updates mode parameter in any method, then the type in question is mutable. Big terminology word there. When we're talking about reference types, we talk about them in terms of whether or not they are immutable or mutable. So we went into this a little bit with XML trees, which I said were immutable because no matter what method you call on an XML tree, it's not going to change the value of the XML tree. Like I can't say XML.number of children equals 5 and magically update the number of children that an XML tree has. It is immutable. It cannot be changed. Natural numbers, on the other hand, are immutable. Throughout the course of the program, their value can change. You can add to it, you can subtract to it, you can divide it, you can raise it to a certain power. It is mutable. It can be changed. Sorry. Okay. In an ensures clause, a hashtag in front of a variable whose value might be changed is pronounced old. So hashtag this simply means the old value of this. So the incoming value of this. So what the value of this was before we called the method. So if n was, say, a reference pointing towards a value of 4, the old value of this would be 4. All right. So, for example, if we have m as 143, and then we call m.add k, what will be the resulting value of m?
213.
213. And what will be the resulting value of k?
70.
Yes. K stays the same because if you look at the contract, you'll notice that even though we have N as a argument, it is not in updates parameter mode, meaning that it is the default, it is restores, it will stay the same. It is not going to be the case for every method that we talk about, so keep that in mind. So M is 213, K remains the same. All right, subtract. Subtracts N from this. Again, this is in updates mode. It requires that this is greater than or equal to N. Why is this the case? Why must the value that we are subtracting from the value, or sorry, why must the natural number that we are subtracting from this be less than this? Yeah. Exactly. If you try to subtract 50 from, say, a natural number which has a value of 49, it would be -1, and that is illegal on so many fronts in the Java language, especially in the natural number case. So requires that this is greater than or equal to N so that you remain above 0 after the method has concluded, and it ensures that this is equal to the old value of this minus N. Important. The method contract could have been written as the old value of this is equal to this plus N, or it could have been written as the new value of this plus N equals the old value of this. As long as it makes sense contractually, you can write it. The easiest way to say it, though, is that this is equal to the old value of this minus N, because that's how subtraction works. And again, notice that N is not in a certain parameter mode, which means that it is restores. So now we have M equal to 143, K equal to 70, and we call M dot subtract K. What is going to be the value of M after this code runs? $73. M is going to be equal to 73. K remains the same. All right, next up, multiply. Multiplies this by N, updates this, ensures that this is equal to the old value of this times N. This one doesn't have any special stipulations on it. It's simply a multiply method. I'm not going to ask what the value of 143 times 70 is. That will require a calculator, but afterwards you can see that M is equal to whatever 143 times 70 is, and K remains the same. That is multiply. Divide is the first one that is a little bit funky. So divide, instead of being a void method like all of the other methods, is a natural number return type. So when you call this method, it's going to return a natural number back to you. And that natural number is going to be, if you look at contract, is going to be the remainder of dividing this by natural number. So if we have N equal to 4, and then we have like T equal to 2, what we do is we divide, and then we call, say, N dot divide T. It's going to take 4, which is this, in this case, in the contract case, divide it by T, which in this case is 2, and return the remainder. In this case, the remainder is 0, but it's not always going to be the case that the remainder is 0. So it's important to store whatever the remainder is in another natural number in case you need it later. Okay, it requires that N is greater than 0. This is for the same reason that we required this to be greater than or equal to N when we were subtracting, because we do not want negative numbers. And it ensures that the old value of this is equal to N times the new value of this plus divide, which is returned back to us, and that 0 is less than or equal to divide is less than N, meaning that the remainder is positive because we cannot have negative numbers. So that's how you read that contract there. Okay, so this code, we're saying the natural number R that we are defining to be a new natural number should be the remainder of dividing M by K. So there are 3 values that are going to appear in this state box after we run this code. What is the value of R going to be, or the remainder? 3, because that is the remainder of dividing 143 by 70. We'll go with this, the easiest one here. What is the value of K going to be? 70. Does not update. And then what is the value of M going to be? Doesn't update either, right? It does. 2. So you take 143, you divide it by 70, you say, what is the result? Well, the result is 2 remainder 3. 2 gets stored back into M. The remainder 3 gets stored in R. Just like that. Okay. That's the one that confuses a lot of people just because you have to store the remainder in a natural number. Okay. Next up is power, raises this to the power of P, updates this, requires that P is greater than or equal to 0, ensures that, who wants to take a shot at reading this contract in English? Like how it would be written or read in English. Who would like to take a stab at reading this contract as it is written? It's like a sip of my water.
Would it just be this is equal to this?
Not just this, but what does that
It's the
hashtag mean?
old this, but it doesn't look like it's the same thing though, right?
What do you mean the same thing?
Because it says this, and the update is just this, so it requires E to be greater than or equal to 0.
Yeah. So this would be read as
The
this
old
is equal
this.
to what?
The old this, or
Right.
to the power of P.
Yeah,
If it's a greater, oh hell yeah.
exactly. This is equal to the old value of this to the power of P.
Okay, cool. I think I was overthinking it because I thought
Yeah.
that I thought the trick was that this is still this.
No,
that,
no,
like,
no, no.
It updates, but it doesn't update.
Yeah,
because
so-
it's just this.
Without the hashtag, it just means that the new value of this.
Okay.
So after the method call is just this, before the method call is the hashtag value.
Okay, I get it. I think I
Mm.
was just I thought you were trying to trick me.
No, 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 no. I would never. I would never. Bucci, on the other hand, when he makes the exams. Okay. Note that 0 to the power of 0 equals 1 by definition of the power operator. So keep that in mind. Okay. I won't make you guys do 143 to the power of K, but it is that. Unless one of you guys is like a savant and can do that in your head, but I cannot. Okay. Next up is root. I guess, fun thing to note about root is that it takes in an integer instead of a natural number. So when you're using it, make sure that you're using an integer, not a natural number. Updates this to the rth root of its incoming value. So it doesn't return anything. It just updates this to the rth root. So if you have 144 and then you pass in the integer 2, it will update it to 12. Requires that r is greater than or equal to 2. And then it ensures, I won't make somebody read this, ensures that the new value of this to the power of r is less than or equal to the old value of this, which is less than the new value of this plus 1 to the power of r. And that is because we do not deal in decimal points when we're talking about natural numbers. So if you try to take the square root of something that is not perfectly divisible or perfectly rooted, I guess would be the term. So if you like try to take the square root of 64, no, I chose the worst example. If you try to take the square root of something like 65, which doesn't have a perfect square root, it will do what Java normally does and truncate it down to the less value. So here's that example. If you take 143 and then you try to take the square root of it, it is a little bit less than 12. So what will happen is it will be 11 instead of 12. But if you try to actually take the square root of something that has the perfect square of 144, it will be the value of 12. And that's why this contract is so weirdly defined. It simply means that it is going to be it is going to be between whatever the less or whatever the lower integer square root is, and then 1 above the square root. So if it's like 12.5 is the actual answer, it's going to be between 12 and 13 is what that means. Okay. Good so far on natural number. Nice. Okay. Copy from copies n to this. New parameter mode just dropped. It is, question.
For the last one.
Yeah.
Why is RNA?
It's a good question. You'd have to ask whoever wrote this, but I would assume because if I had to make a guess, I'd say that it's probably hard in the actual implementation of how root works to use a natural number to do the square root, and it's a lot easier to do the integer. So they thought, let's just use an integer. So laziness is actually the correct answer there. Which is, if you ever have a question about why somebody did something, it's probably laziness. Okay. Replaces mode is the newest parameter mode that we're talking about, or that drops. Replaces mode simply means that the value might be replaced. I believe there's another stipulation, but I forget what it is, but the slides will provide. Okay, parameter mode replaced in a contract means that the variable's value might be changed by a call to the method, but the new value is independent of the old value. So this is different than updates because in an updates mode parameter, you'll notice that they both say that they might be replaced. So maybe updated. In an updates mode parameter, though, it depends on the old value. Whereas in the replaces mode, it is independent of the old value. And the way that this manifests, independent of, well, the example you can use to differentiate between the two is that add is an updates mode parameter because when you're adding something to a natural number, it's going to depend on what the old value is. If I add 70 to 4 instead of 3, the new value is going to depend on whether or not that original value was 4 or 3. And copy from, which simply just transfers the number, it doesn't matter if my old value is 4 or 3. I'm overriding it anyway. So it doesn't matter whether or not it was 4 or 3 or a million or 100,000 billion, which you can do in a natural number. It's going to get overwritten, so the old value does not matter. That's the difference between replaces mode and updates mode. Okay. If this is a replaces mode parameter in any method, then the type in question is mutable. It has to be because otherwise you can't change the value. Again, mutable meaning that it can change over the course of the program. All right, so if we have m and k, and then we say m.copy from k, what is the value of both m and k going to be after this method call has run? 70. Okay. Compare to is very similar to the compare to that we've used before. Have we used before? Compare to is something that you will use a lot, and here's how it works. Compares n to this, returning a negative number if this is less than n, 0 if this is equal to n, and a positive number is if this is greater than n. So if we have two natural numbers, say, we have two natural numbers, n and t. We have n dot compared to t. The way it works is you take this value and you take this value and you determine whether or not n is less than, equal to, or greater than. So if it's greater than, then it's going to return 1. If they were equal, let's say that 4 and 4, then it's going to return 0. And if it's less than, it's going to return negative 1. So the value that we care about is the value that it is called on. That is the value that we use when determining whether it should be 1, 0, or negative 1. This is less than, yeah, so negative 1. I guess I flipped it, but same thing works. If it is less than, it's going to be negative 1. If it is equal to, it's going to be 0. If it's greater than, it's going to be 1. Notice it says a positive number. We always use 1, but it could return any positive number, technically. These are known as like comparators, and you will not have to write them, but if you did, the general formula is that it has to be negative if it's less, 0 if it's equal, positive if it's greater than, and you could technically return like 42 as your positive number, but we're always going to use 1, 0, and negative 1. Okay, so in this case, we're saying m dot compare to k, 143, we're comparing that to 70. That is greater than, so the value is going to be equal to 1. So the comp is going to be 1. And the comp is going to be an integer. Though here the result of the method is 1, it could be any positive int, so don't assume it's 1. So when you're working with comparators, and you're working with the compare to method, don't say dot equals or equals equals 1 just because you think that it's going to return 1. You should check if it's positive, negative, or 0 instead, because it could return any value. It's not going to, but it's best practice too. Okay, that's compared to. Questions? All right, now we're getting into the kernel methods. Again, these are the minimum viable methods needed in order to implement a natural number. We have multiply by 10, which multiplies this by 10 and then adds k. The reason that we have to add k is because if we did not add k, you would only be able to work in multiples of 10, and that would be a very boring program. So requires that 0 is less than or equal to k is less than 10. And then the new value of this is equal to 10 times the old value of this plus k. This is a kernel method. Thank you. Okay. So we have m equal to 143. Essentially, what it does is it takes your value, 143, it adds a 0 onto it, and then turns that 0 into whatever you passed in. So 7 in this case. So I would ask what the value is, but we just did it. It's going to be 1437. Yeah. Hopefully nothing like groundbreaking. Now, the older brother of that, or the younger, depending on, maybe they're twins, is divide by 10, which divides this by 10 and then returns the remainder. So if we call it divide by 10, we set it equal to, say, int L equals 147. Imagine this is divide by 10. L would be equal to 7. And the natural number would get updated back to being just 143. It just chops off whatever the right value is and returns that as an integer. And the reason we're allowed to return it as an integer is because it's only ever going to be between 0 and 9. It's never going to be greater than the integer limit. This is also a kernel method. So R equals 1437. The trick is to just chop off the last digit, and that is what is going to be the value. Also not groundbreaking. Is 0, super fun method, returns whether or not this is 0. Is there even an example? There is. Okay, is 143.is0 will return what? True or false? False. Okay, 2 of us are weak. Now, let's say m was 0. What would is0 return? True. Awesome. Cool. Okay, questions on is0. I know it's a toughie. Okay, clear resets this to an initial value, clears this. Uh-oh, new parameter mode. Gotta erase this. Natural number. Clears. Clears. To some initial value. Notice how it doesn't say 0. You could write an implementation of natural number where it clears the value to like 47 because it's your favorite number. But we're not going to do that. That would be stupid. Clears, in this case, will return the natural number to being just 0. Ensures that the new value of this is equal to 0. This is a standard method. So you can call this on any OSU CSE component, and it will return it back to an initial value. So natural number is going to be 0. If you had, say, like natural double, it would I assume it would be 0.0. If you call clear on an XML tree, I'm assuming it just wipes the XML tree, so on and so forth. Whatever the initial value is. Parameter mode called clears means that the variable's value is reset to an initial value by a call to the method. If this is a clears mode parameter in any method, then the type in question is mutable. It can be changed. The ensures clause is redundant in this case because this is a clears mode parameter. So yeah, write the ensures clause and then say that it's redundant. Okay, 143 is equal to m. We call it m.clear. What will the value of m be after the method call? 0. Perfect. Okay, new instance returns a new object with the same implementation as this, having an initial value. So same implementation in this case simply means whether or not you're using a natural number 2 or a natural number 1L. So it returns a natural number of blank value, but it's going to be the same implementation type as whatever this is. So if I call, or if I have a natural number 2, and I call new instance, it's going to return a natural number 2. If I have a natural number 1L and I call new instance, it's going to return a natural number 1L. This gets really important for sometimes if you're writing a static method, you'll say that you want to pass in a natural number and then you want to make another natural number in the method code. you can't just guess and say, well, I think the user is going to pass in a natural number 2, or I think the user is going to pass in a natural number 1L. Because then the user passes in a natural number 1L, and you guess that they would pass in a natural number 2, and then you try to mix the two. They do not go together. But if you call new instance, then you can just always create a natural number that is of the same implementation type as whatever is passed in, which is nice. And this is a standard method, so you can do this with anything. Similar to a constructor, the difference is that you don't need to know the name of any implementation class to call this method. So if you have, this is like cloning, basically. You just clone a natural number, and it's of the same type. So if you clone a natural number 2, you get a natural number 2. If you clone a natural number 1L, you get a natural number 1L. So M143, K equals new instance, you have some initial value. Notice that it doesn't copy the value, it simply makes a new natural number as if you called a constructor. The only difference is you don't need to know any of the implementation class names, which is nice. Okay, transfer from sets this to the incoming value of n and resets n to an initial value. N must be of the same implementation as this. So we have 2 parameter modes in this case. This is replaced, which means that it may be updated. It is independent of the old value, so it doesn't matter what the value is if you're transferring into a new value. And then we have a clears mode parameter. People forget that n is clears mode in this case. So if you have 2 natural numbers and then you call clears mode, or sorry, you call transfer from, the value of that second natural number that you're transferring into the value is going to be 0 afterwards. It's not going to keep its value. So it ensures that this is equal to the old value of n. It's the old value of n because the new value of n is 0, or whatever the initial value is. And this is a standard method. Similar to copy from, but it is always more efficient, so it should be used if you don't really need a duplicate. So if it doesn't matter that n is going to be, or yeah, it's called n. Is it called n? Yeah. If it doesn't matter what n is going to be after the method call has been run, you should use transfer from. Because we're basically throwing it away. Doesn't matter anymore. So m equal to 143.
One more time, I'm sorry.
Yeah, so if it doesn't matter what the value of the natural number that you're transferring into this is, you should use transfer from.
Okay.
But let's say that n was important and you needed it afterwards, you shouldn't call transfer from because it's going to delete the value. I guess you still have it in the new natural number, but if you needed a copy, or I guess if you need a duplicate of it, then you should call copy from. So m equal to 143, k equals 70. We're calling m dot transfer from k. What will the value of m be after this method call? $70. And then secondary question, follow-up question, what will the value of k be? 0. Perfect, because it's clears mode. And then, whoa, it clears n. Did you notice that transfer from changes the value of its argument? Hopefully. How can it do this? Didn't we just say that this can't happen? It can't for arguments of Java's primitive types. So a big thing that I kind of hammered into you guys during the first part or the first third of the semester was that when you're passing in variables or you're passing in primitive variables into a method and then you change them within those method, it doesn't change it outside of the method. And that is true only for primitive types. So we're entering a new world now where the value can be changed. And the way it can be changed is because instead of storing the actual value here, we're storing a reference to the value. And we'll get into a lot of this later, but this is a teaser. This is an end credit scene of today's lecture. Crucial difference between Java's primitive types and all other types that allows this behavior for other types. Details coming soon. Again, end credit scene. Okay, 3 more slides. ToString returns a string representation of this. Take the natural number, turns it into a string. 143, 143. Okay. That's it. Any questions about natural number? I think tomorrow's lab is on natural number, so get excited. The midterms will probably be back Thursday. They will be. I have to have them back by Thursday, actually. So they're going to be back by Thursday. All right. You are dismissed. Have a good Tuesday. Tuesday? Tuesday.